Good morning, ladies and gentlemen. My name is Alexandra Maslakova. I represent the team of Russian Federation and I'm going to present you our solution to problem number 1, sound thermometer. Here is the statement of the task. Devise a method to obtain the temperature of a fluid by listening to the sound produced when it's poured into a cup. State the precision, accuracy and the limits of your method as well as the important parameters of the fluid. Sounds. Let's listen to the sound of hot and cold water. Oh, they don't play, so just play the sound. First must be hot. And this is cold water. So we'll start with a theoretical explanation. This is the spectrogram of sound of pouring. Spectrogram shows how spectrum of sound changes over time. Here we can see one fundamental frequency and its high harmonics, and noise at some frequencies. So let's find out what emits the sound. This is water on 25 degrees Celsius, and this is glycerin, and we can't hear any sound. Yes, you're playing. Sure. We can't hear any sound, so we make a conclusion that the only sound emitter, the main sound emitter, are the bubbles that are produced during pouring. So let's investigate their sound. There are some types of sound that bubbles can produce. First is oscillations, the volume oscillations, which is called minute resonance, and we can find the resonance with this formula. And some bubbles produce oscillations of surface, but only small ones, because the big ones oscillate on very low frequencies. The other sound that bubbles can produce goes here. Sometimes we can see that first the column appears, then it collapses and divides into a bubble and another column oscillates with this frequency as a resonator, as a pipe with one sealed end, and the bubble resonates with minute resonance frequency. Here are our theoretical estimations and experimental results, and you can see that they are in a good agreement. Okay, so when we pour a liquid into a cup, there are a lot of bubbles that are produced, so we made a screenshot and found the diameters, or well, radii of the bubbles that are produced, and this is the distribution of bubbles radii on actually this picture. Then we generated spectrum using the minute formula presented before, and this is the generated distribution of frequencies, which is basically a spectrum, and this is real spectrum that we got. We can see that these frequencies are almost the same, and this frequency we make a conjecture that this is the frequency of the sound produced when the columns appeared, as we stated above. Okay, so now let's go to the difference between hot and cold water. First, we made a spectrum averaged over all the pouring. And we can see here some peaks that appear in cold water and don't appear in hot, especially this one. And we make a conjecture that these peaks are the peaks of natural frequency of walls of the glass. So we conducted the following experiment. We heat the cup during pouring. This is hot water. You can see that these frequencies disappear and never appear again. And this is cold water. And you can see that frequencies shift. Of course they shift, and but they never disappear, just as we see on the spectrum. So to verify this, we conducted the following, the same experiments with another types of vessels. This glass jar, we still can see the peaks, but they are not that big. And we use the plastic cylinder, and we can see no difference between hot and cold water sound, because the Q factor of the walls of plastic Q factor is low. So let's go to this spectrogram again. And since the method that we used before is not good, because the dependencies are very small, differences are very small, and so we decided to use something that we can see on the spectrogram, because it's more visible and easier to investigate. So, what are these lines? the air between top of water, between surface of water and top of the cup resonates as a pipe with one sealed end, and it produces odd harmonics. We measure the sound. All these harmonics are odd, and the fundamental frequency corresponds with this formula, where C is speed of sound in the air, and L is basically length between the top of water and the top of cup. So it's very well known that speed of sound depends on temperature as square root, and the difference in our working range between 0 and 100 degrees is considerable. So basically, what is the phenomenon that we base our method on? When hot water is poured into a cup, it heats the water due to convection and evaporation. Speed of sound increases with increasing of temperature, and fundamental frequency of resonator increases as well. So our method is just going backwards, and I'll explain it later. So here is method of measurement. Here is our experimental setup. We pour water in the water tank using the tap, so we can control the speed of flow. You can see it here that it's constant. We, of course, recorded the sound with a microphone, and this is the vessel that we used. We can see on the spectrogram the beginning of pouring, so we can choose the range of heights that we can investigate, and they are the same during every experiment because the flow is constant. And we also can change the nozzle of the tap. So what we did is we recorded the sound, then using Wolfram Mathematica extracted fundamental frequency from the sound. You can see it here. Then we made a dependence of frequency on the length of the water, and then we found the speed of sound in this case, and then, well, we made it for every temperature, well, for a lot of temperatures, a lot of times. Here are our graphs. So this is speed of sound over temperature, and this is measured temperature over real temperature. And what can we see here? I'll explain these dots later, but these two ones are slightly above the theoretical line because due to evaporation, speed of sound increases even more because speed of sound in the vapor is more than speed of sound in the dry air. Okay, so now let's go to investigation of accuracy and working range of our method. First, the main condition to for our method to work is presence of sound. Surprise, surprise. And for sound to be, we must have bubbles, as we said before. And to form bubbles, well, if the jet of the water is turbulent, the bubbles always appear. And if it's laminar, it can divide into droplets due to Rayleigh-Plateau instability. And in capillary case, it goes like here, and in viscous case, it goes like here. And the minimal time for dividing is either of these two. Okay, there are some sources of errors. Q-value of resonance chamber and irregularity of water surface affects the random errors, and systematic errors are heat conduction and heat loss. Heat loss is when we pour hot water in the cup, it basically cools down for like several degrees. So, quality factor of resonance chamber shows the width of peak, of resonance peak, and the more the Q factor, the more accurate is frequency determination. These are spectrograms of two different vessels with different diameters, and here is the dependence of accuracy on the ratio of diameter over the length. Irregularity of surface influences just as the Q factor. We can't measure the temperature very precisely. Systematic error due to heat conduction, you can see it here. This is the line for 50% glycerol solution, and it lies in below the theoretical line because the walls and air in the because air in the cup heats slowly, so the measured temperature is a little lower than the theoretical one. And here are our conclusions. Sound is produced by bubbles and filtered by resonator in the cup. We can hear difference in hot and cold water because of scattering of sound on bubbles of water, blah blah blah, and accuracy is ±5 degrees for water. Systematic error due to heat conduction is -12% for water and -23% for glycerin solution. Thank you for your attention.
again. I'm Paweł Szybkowski. I represent the team of Poland from University of Warsaw, and I've got this pleasure to oppose your really great presentation out of the sound thermometer. Maybe let me get again the statement of the problem. You have devised the method, yes, that's sure, to build this thermometer. You state the precision and the accuracy limits, but really I'm not sure about this accuracy, what I will show later. Well, I didn't hear anything about the important parameters of the fluid, like you've said about this proper number, which of course is dependent out of the surface tension, but still I get the lack of stating that the importance parameter were this, this, and this. So this would be the thing that I would like to discuss, and also what you've done during your presentation. You explained the phenomena, even though I think this explanation, well, it was good, but still, and sometimes it's not consistent. To which point I will go later. But you've built this thermometer, and I don't know really how does it work properly, but it would turn out. And about this accuracy, because I've also tried to do this, and with the same thing as the let's say difference between speed of sound, and what I got is completely different accuracy. Because let's assume that the speed of sound is some constant and the square root of temperature. So if we got this odd number of modes and the frequency that we can check, we can also have the dependency over frequency and the temperature. So while we'll be expanding the square root into the series, we would get something like this. And what I had with my with this expand is that to obtain the accuracy of 50 degrees, you need to have accuracy of the frequency over the 5 Hz. Having such a wide range of sampling that you have in your spectrogram, it's not, it's impossible to have such accuracy, because you also, what I would like to ask you, you also didn't tell about the flow rate, because here the frequency also depends on how fast do you pour the water. So what I would like to also say is that when you're pouring the water, the surface is not like flat. You cannot tell, well, it's flat, and I can estimate that the standing wave is just on a flat surface. Okay? You cannot do that because here you've got turbulent flow, as you said. So what also would be the next question for me is really that you have seen that the frequency shift is in the right direction, because when I hear the water falling, I hear the sound which is lower, and from your theory, from your explanation, the sound should be higher. And I think we have to, during this discussion of semi-final, we have to explain this phenomena at all. Okay, thank you for your attention, and I guess so please, first of all, I would also like to see your answer what's really the difference between the sound?
Okay, as you have said that we can hear that sound is lower in hot water, but
So what's the main thing between them? Why it's lower?
we calculate the bubbles radius distribution.
Can you see? Can you show me that? That bubble distributions.
Okay. Wait a little. So basically, in hot water, the bubbles are usually bigger.
Just show.
I have to press escape and it doesn't work. So we have to wait.
Okay, about bubble distribution.
So in case of hot water, please help me. In case of hot water, the bubbles are bigger. So there is a slight shift in frequencies to the low.
Why are they bigger? Did you observe that experimentally? Because you've measured the radius of the bubble.
You know, this is not the phenomena that I have investigated, because accuracy in this case would be worse than we have obtained.
So why, if the sound is lower, so why have you been measuring the thing that indeed hires the frequency of the sound? It's like contradictory.
Okay, statement of the task doesn't ask us to measure the sound by hearing it, and what we hear and what we can measure are two different things. So we hear one thing that is very hard to measure.
So why we hear the lower thing? Because you were telling me that because of this bubbles distribution, yes, the sound frequency from the Meiner's formula, yes, from the formulas for the bubbles are lower, yes?
Excuse me.
Could you please go to the Meiner's formula? Yes, this one. So you've said that for the bigger bubble, as we can...
No, here.
Okay. So what is the dependency here on the temperature in this frequency?
So the bigger the temperature, the bigger we'll get the radio.
Okay.
So if the radio are bigger,
and what's the difference between the radius?
I can't say we didn't investigate the distribution on the temperature.
Okay, and maybe you could make a guess what the distribution will be.
I have already said that in the hot water case, the distribution will be shifted to the left.
Okay, and maybe you were wondering how much it would be shifted, because...
no, I can't say, but I can say that it's not a very much difference to build the method on, and I think your question about accuracy is more interesting than question about the distribution of radii in hot water.
Honestly, I will leave the accuracy thing to the reviewer, okay? Because I think the most important is to explain this phenomena, why we can hear the lower voice.
Okay,
this is the point of
there is one interesting thing we have tried. We took a sound of cold water, and using equalizer we just cut off all the high frequency. And we got a sound that was like kind of hot water, but a little bit artificial.
Okay, so what cuts the higher frequency then?
Rayleigh scattering, as I've shown on the on these slides. Since the scattering depends on frequency as frequency to the 4, higher frequencies just scatter.
So you need to have the scattering. You need to have, for example, a cup. If you do such in, for example, wider.
Yes, we've tried this, and actually, if we try a vessel that has no resonance of walls, we barely can hear the difference between hot and cold water.
Okay, and do you have an idea why is that? Why is that?
Maybe you can answer.
Okay, this is because the resonance of walls influences this as well.
Hello everybody, my name is Ricardo Gitti. I'm gonna be the reviewer from Team Brazil. So on the sound thermometer problem, we have the highlights of the reporter is that they showed the hot and cold sounds, spectrogram analysis of the sound, and water and glycerin sounds, which is quite important because the difference of each liquid. The minor vibrations of the bubbles, which it's the important one that they have said. Schematic images showing the different parts of the problem, the bubble and water sound differentiation and spectrum peaks. They have studied the one-end closed tube, varied the size of the chamber to see with this relation. Amplification of the sound due to different chambers, also a consequence of applying this one, and a related changes in temperature of air with change in sound velocity. And also some remarks, are bubbles just an evidence of the most important factor, or there is another factor that is pretty important? Did not mention also the influence of the initial flux. It's that laminar or turbulent. Is there any difference during this? It's something that we can discuss. There is some highlights to the opponent also. He brought out the importance of the sounds, speed influence on the function of temperature. He also brings out the surface and turbulent flow when pouring water. And he has questioned the error measurements in the reporter's problem. And now some remarks.
I'm sorry, let me just stop it. Alexandra, no communication with the team.
Oh, I'm sorry. Some remarks to the opponent. It has a confused some technical questions, so there are some important points that we want to discuss now. He did not question the importance of the energy changes, water from water. Is that only bubbles? Is that another thing that's happening? Let's start from this. He has mentioned errors, but does not propose a method to improve it, which is quite important, but I believe it's the lack of time, so we can do it now. I'm not clear if the water fall influences the error, the transient regime, it will influence the error too. So, about the discussion, we like to guide the discussion talking firstly like this. Only bubbles are the way to exchange energy in the system. Can we separate the phenomena that are happening and only analyze bubbles? Can we discuss the precision of the method due to what they have measured? Is there the sensibility always constant? Which is the importance of it? How can we get a better accuracy? And what's the importance of the linearity, the measured and the obtained by the method? So we have to extrapolate also the solution for a fluid in permanent regime. Is that possible? Or what can we have to change to make with different kinds of liquids which also have great importance, not like glycerin as he said. So let's start the discussion, please, if you want.
May I have one remark?
Excuse me, we just estimated the error just as opponent proposed us, and we got the error not 50 degrees but 7.4.
Could you please show the derivation?
I can show it to the jury members. I think they are more interested in this than you.
Okay.
And we can go to our discussion.
But please, the importance here is the origin of the sound. So you have analyzed bubbles. You have agreed or not even try to refuse. So is that only bubbles important? Please, the reporter.
Bubbles, well, we stated that not only bubbles can produce the sound. Our since we investigated the resonator between the water and the top of cup, it doesn't produce sound, but it filters it. So only bubbles produce sounds. We could see it on the videos with glycerin and water.
Great.
No bubbles, no sound.
Yeah.
Okay,
about the opponent, what do you think about the bubbles? Firstly.
About the bubbles, yes, they are creating a sound, and you can hear it by just making the bubble in, for example, a bath, and you can hear the sound. And there are lots of simulation are based on the bubbles. So yes, that's
another important one, probably more important. Do you think one of them, or is just bubbles?
No, it's not just bubbles, because having only bubbles you cannot make the same sound as pouring. And
okay.
by the way, could you please move to the slide number 7?
I'm sorry, just slide. Can we just finish here? I have one experimental imagine one.
One remark, because here you've got a formula, and here you've got a number mode 1, and for number mode 1, the frequency is 0.
I know, we calculated starting from the second, third, and then. so on.
Uh,
Not the first one. It's just
So
animation.
for what purpose is the first one?
I understand, but please,
To investigate all the sound.
to talking about the bubbles, firstly, that's what's one last point. If you get a straw and you blow it inside the cup,
Yes.
it will generate bubbles.
Yes.
Yes.
Imagine
that's
that you can use a straw to say the same radial size and the same amount of bubbles.
Okay.
It will be the same noise.
No.
It will be the same what?
It will be the same noise that we hear from here.
No, it's not the same noise. But yeah.
What's not happening that it can be
Actually,
the
we made
origin
this
of noise?
experiment as well, and we could see that well, if the bubbles are all well, they were not all the same size, but they were quite close to each other, and there was a shift of frequency. So the hotter was the water, actually the higher was the mean frequency of them. So frequency increased with increasing the temperature.
I understand.
And this is why we don't agree with the opponent that well, this formula that we can base it on this formula, because this formula gives it that the more temperature, the less is frequency, but experimentally the frequency is always bigger because of the changing of speed of sound.
Do you know what's the origin of this formula? What it's from? Because here you've got a gamma. What's the gamma? Here.
Adiabatic coefficient.
Okay, and here you don't have one. So, like, the thing that's happening is way different. And do you know the difference between the higher modes and not spherical bubbles and the spherical one?
Okay,
do you know
so
the difference?
you answer, please.
What is the difference?
Yes.
Well,
What's the origin of that movement and what's the origin of this movement?
I can't say it now, and I don't think it's important.
Okay, thank you.
Okay, so about going to another question that we have lack of time. What's the sensibility of your system, and why sensibility is important? Is that linear?
What do you mean?
What do
by
you?
sense-
Okay,
what do you mean by
sensibility is like
The
We have
team
another
may now
whiteboard.
join in the discussion as well.
Okay, so right before just finish this, when you have an increase of your x-axis, which is frequency, how much does temperature increase? Is that linear? Is the sensibility
no.
of your sensor?
It's not linear. You could see it on my plots. I think it's.
You've seen that the square root is linear in your range. So
I mean that experimentally we got the something like this for slow evaporating liquids, and something like this for good evaporating.
Okay, so the sensibility will be quite different because there is no
Yes.
linear. What's the importance of having a linear one, and what will be the difficulties of the reporter to have a non-linear? Can you say the opponent?
yes, the linear scale is that good that we can just measure one point, have one point of reference, and we know that. Non-linear, we need to have more of them.
Okay,
So
so
it's
let's
basically the
open.
systematic error, so we can just add or distract it.
But
Understand.
You have to
So
have a
let's
great
open,
theory
please.
to
Yes.
Excuse me. So let's open, please, to the Russian team.
I would like to make a slight comment about the slide. Firstly, the number
Yes.
mode on these pictures, of course, 2.
Yeah.
And,
Okay.
It's just a mistake.
And the set, it's just typing error. And second, this formula is the classical formula for the surface oscillation of the drop or bubble, and the first formula is the for the oscillation due to pressure difference.
Yes.
Is that what we want to hear?
Actually, this formula comes from solving the
On the
Navier-Stokes.
surface oscillations, the classical formula.
But
you write
we'll
the
write
formula
nominal
and
and
thus you get
It's from solving the Navier-Stokes equation of a fluid inside the fluid.
You may write it simpler from simpler Lagrange, and this formula can be from the thermodynamic equations.
Okay, the thing is, the origin of these two oscillations are quite different, and also I don't know
Okay.
what do you think about pumping energy into the different modes?
Understand. Remarks from other teams? No one. So the reviewer.
If the permanent region is important to the change in the phenomenon, what does it actually change in the phenomenon for both the reporter and
Okay,
the
I can answer that. It actually, if we have a permanent regime, it will be even easier to us to measure this, the temperature with our method, because what we did is we tried to find the speed of sound on every point of time, and now we would just have the same height, and we will have less work to do.
Okay, thinking so on the same question, they have used to the opponent. They have used in closed tubes formula, so it makes a difference from how much water lacks on the tube. So in a permanent regime, what will change on the spectrogram?
Excuse me, could you?
In a permanent regime, what will be different in the spectrogram? That's why we have questioned it. The frequency, how will it be different in every time, for example?
I've said the difference in frequency from the different temperatures would be about 5 hertz, so it's out of the measure.
Would we be able, the frequency is something like this, the most important one, there was an increase in here.
Yes.
Would we be able to see this increasing of frequency in a permanent regime?
Of course not.
Yeah, okay.
I think my team has comments.
Comments to another one, do you have?
No, just the frequency will be constant.
Yes.
The frequency will be
just as I said.
constant. Yeah, okay. To the opponent? No? So the reviewer, please.
As you pour water on the vessel, on the glass, the frequency changes with time, right? So I wanna ask, did you consider the sampling ratio of your microphone to estimate the error?
We didn't include our microphone characteristic into investigating error because all errors were investigated mostly experimentally. So what we got.
Yeah, it was certain. So we are in lack of time, so if it's very shortly.
Have you used this algorithm to measure the real temperature of something, and you have this algorithm of yours of measuring this thermometer to measure the temperature of something you don't know? And
Okay.
Yes, of course.
That's right. Okay, last question. Do you think the reporter gave a complete solution? Yes or
Time is
no?
unfortunate.
No.
And for you, what would be better?
Time is up.
Time is up. Time is up.
So, concluding remarks by the reporter.
Okay. Thank you very much. This was pleasant fight, and what would I want to say is that I might have been not clear enough, but I think the method that we presented is good enough to measure temperature of sound, and these things were just to know how the sound is produced, what actually happens here in the problem, and our method is based on quite different things, and I think you understood this, and well, the discussion was very interesting, so thank you.
So, we move to questions from the jury, and before we start, I will say that I will give each jury member one question. Please try to stick to it so that we can have the whole jury members who wants to ask one question can ask one question. If there's more time afterwards, or some jury members doesn't want to use their one question, then you can ask more questions then. Okay? So we'll start with Susanne.
Yes, I want to ask the opponent and the reviewer, in the presentation and the ensuing discussions, do you guys feel like the questions of state the precision, accuracy, and limits of your methods, as well as important parameters of the fluid, was answered?
Honestly, no, but as I've said, for me it's way more important to understand what's really happening here and why we are hearing the lower tones, and the physics that we've presented here told us that we should hear the higher ones.
They have presented values for accuracy and precision. It should just be a little bit more clear of how they have they and how does it change. It will be very interesting. About the important parameters, I believe that they have get just one and focused on it, and I have questioned it to think about other ones that could influence and change precision and accuracy. And about the method, I believe that the method is quite good. but I try to raise up some questions to improve the method in order to reduce the precision. So I believe that half of the questions was very well answered, and some of them probably because the lack of time, or also because the lack of clearly. So.
I'd like to ask the opponent and then the reporter, what is your answer to the question, why doesn't this method work with glycerin?
Because the glycerin doesn't make bubbles.
Why?
Because when it's hitting its surface, there's no turbulent flow out here. Glycerin, because glycerin has high viscosity and also higher surface tension, and that's why it doesn't form the turbulent flow.
Okay, this method works with glycerin on temperatures above 40 degrees, because in 40 degrees it starts to form bubbles. And yes, I agree with the opponent, viscosity influences the appearance of bubbles.
Do you understand, reporter, do you understand correctly that the signal you're using is the sound produced by the air between the surface of the liquid and the top of the cup?
Yes.
Right?
Not produced. But
So, what is actually the temperature you're measuring? Which temperature are you actually measuring?
Temperature of the air above the water, but we assume that it's equal to the temperature of water due to fast heating, actually. So it's roughly the same.
Okay. Any other questions from the jury?
Yes. How the temperature for the presenter, how for the reporter, how the fact that the glass is open on the top will change? Cannot it cause temperature gradients that affect your measuring?
Excuse me.
You have an open glass, no? So you will have temperature gradients. Can these temperature gradients affect your measure?
Yes, of course they can. I stated it on the errors due to heat loss and heat conduction.
And how much is it? How large are these?
It depends on the temperature of the water. So the more the temperature, the more the difference between them, and precision is the difference between measured and real temperature is bigger.
Were you able to quantify these errors on the inaccuracy due to temperature loss experimentally?
Due to temperature loss,
Did
well,
you just
it's not
assume
precision. It's precision. The temperature change does not affect accuracy. In our case, it affects the precision. And yes, we did. I've shown it on the conclusion slide.
I mean, did you estimate those values experimentally or theoretically?
Both.
Okay.
David, you can pose a
Yeah.
question here. So.
Just out of curiosity, did you try a liquid on the other scale, so the opposite to glycerin, something which produces many more bubbles?
Yes, things like acetone, alcohol, but we found it a little bit dangerous and smelly to measure higher temperatures.
Why did you say that this formula on the left gives the wrong temperature frequency behavior?
Well, not wrong, but it gives right estimation for frequency if we have one temperature and different sizes of bubbles, but experimentally, if we change the temperature, this frequency of one single bubble increases. It doesn't mean that this formula is wrong. It just means that the phenomena is other than this.
But density and capillary change with temperature. Both density and
Yes, of course we consider this, but still, even if we change pressure and density, what we have done, this formula gives that the hot water has lower frequency than cold.
Okay, thank you. So I think with that we can let the participants go back to their teams.